Hydrodynamics is the study of moving fluids. And to keep things simpler, we are going to deal with what is called a so-called ideal fluid. An ideal fluid is one that is less complicated than most real fluids. If we tried to study like honey that's super sticky or something like that, it can become really problematic. And so an ideal fluid has a couple of properties that you need to take note of. Number one, the fluid is non-viscous. It's not thick. It doesn't resist flow. It doesn't have internal friction. Number two, it is incompressible. So we're not going to be dealing with air and things. We'll talk about those briefly, but in terms of math and stuff, we'll definitely be sticking with water. You can take a balloon and crush it easily. You take a balloon and fill it with water, you can't crush it. Fluids are generally incompressible. They might be very slightly compressible in real life, but we're going to pretend they're completely incompressible. Next, fluid motion is steady. What we mean by that is any system that we're going to be studying, we're going to say that at any given point, if you've got a pump and then some gravity and then it flows down and it goes through a pipe and a tube and a this and a that, at any given spot, we're going to say that the flow at that point is going to remain constant over time. So whatever is happening there is going to continue to happen there throughout the period of study, throughout the problem we're trying to do. And finally, the last thing is that in an ideal fluid, there is no turbulence. Turbulence are all those vortices and whirls and eddies and stuff you get in real life when you just move your hand through the air or drive a car or an airplane. And so all those little whirlpools and whirlwinds and stuff can cause huge issues in terms of trying to figure things out. So like a whitewater rafting river, very turbulent. The opposite of turbulent flow is laminar flow. And laminar flow is nice and smooth and easy, and we're going to stick with laminar flow for this class. If the mass of a fluid is constant and it is incompressible, that means that its rate of flow is going to remain constant in a system. And so that means if you take a fat pipe and then you compress it down to a skinny pipe, in order to get the same amount of fluid through in the same time, it's going to have to speed up. This is called continuity, and it's really a consequence of conservation of mass. And let's take a moment and derive what we call the equation of continuity, which is on your reference tables and is very useful.
This derivation is fast and easy, and it goes like this. Your volume rate of flow, represented by the Greek letter nu, is going to be equal between the two parts of the pipe. That's volume over time equals volume over time. Volume is going to be the area of the pipe times its length. So area times length over time equals area times length over time. What is distance over time but velocity? So A1V1 equals A2V2 is the equation of continuity.
We use this idea of continuity all the time in fire hoses, for example. You have a big fat hose and it compresses down to a tiny little nozzle that causes the water to shoot out much faster. You've done that if you've ever tried to spray your friends with a garden hose and they're just a little too far away. What do? You put your thumb over the end in order to constrict the area. That creates a greater velocity. In engineering and architecture, we will build things to create breezeways. You can have strategically placed buildings or trees or things to funnel air and cause places to have a greater amount of wind than areas around them. Sometimes that's accidental, like in the quarter mile at RIT or at SUNY Fredonia, where they created breezeways in places that are already pretty windy, and they created some pretty unpleasant experiences for freshmen and sophomores and juniors and seniors who maybe aren't prepared for winter weather with extremely strong breezes in their face as they're trying to go to class. Continuity is also useful with rockets. When you have a rocket and you want it to expel fuel as fast as possible, to expel exhaust as fast as possible, then you constrict the rocket nozzle so that the exhaust is funneled out through a small hole, and that causes it to come out much, much faster. Again, that's dealing with a gas, so it's not exactly the same, but it is the same idea. So we can build something called a Venturi tube. This is useful for measuring fluid speed or measuring fluid pressure. And a Venturi tube looks like this, and you can see that you've got lower pressure where the fluid is faster. Lower pressure where the fluid is faster. Interesting.